Now let's learn about solving a system of equations by substitutions. Now let's pretend you have a system of equations and you want to know where the two equations, or where the graph of the two equations intersect, if they intersect at all, or if there is a solution. You don't have any graph paper or you don't feel like graphing it. Well, all hope is not lost. We can still solve this system by substitution. In other words, we are going to take the expression for one variable and substitute it into the other equation. So here's an example. Y equals 3x and x plus 2y equals negative 21 constitute a system of equations. Now we can see that in the first equations we have expression for y equals 3x. And in both equations, the variable y is the same y, and the variable x is the same x in both equations. If we look at this first equation, we have y equals 3x. So I can take that expression for y, substitute it from the first equation into the y for the second equation, and rewrite that second equation. Every place where I see y, I'm going to write 3x. So now I have x plus 2 times 3x equals negative 21. And we can see that I substituted 3x for y, hence the name solving by substitution. So when I simplify, I get x plus 6x equals negative 21, or 7x equals negative 21. And I divide both sides by 7. I get x equals negative 3. Now I know what x equals. I can take that value for x. Let me choose a different color. Take that value for x, which is negative 3. Bring it back up here and substitute it into either equation for x and solve for y. Now I'm choosing y equals 3x because it is easier. There's less math to do, but this will work with either equation. So y equals 3 times negative 3, or y equals negative 9. So my solution for this system of equations is negative 3, negative 9. Now that seems all relatively easy and painless. But what if your equations aren't written out so easily? In other words, what if they're not expressed in a way that makes it easy to substitute? Let's take a look at this example, this system of equations. X plus 5y equals negative 3, and 3x minus 2y equals 8. So in this one, we don't have an easy expression for either variable in which we can substitute into the other equation, or that we can use to substitute into the other equation. But if I look at this first equation, I see I've got x out here all by itself. So if I can isolate x, in other words, if I can rearrange this equation in terms of x, or solve it in terms of x, then I have something, an expression for x that I could substitute into the second equation. And the way I want to do that is now by getting rid of this 5y. So let's subtract 5y out from both sides of that equation. Now I get x equals negative 3 minus 5y. So, we see we have an expression for x. X equals something. And that something, negative 3 minus 5y, I'm going to insert for x in the second equation. So now let's rewrite the second equation. 3 times negative 3 minus 5y minus 2y equals 8. I see I have some distribution going on here, so I'm going to distribute 3 to both terms in the parentheses and get negative 9 minus 15y minus 2y equals 8. Scroll that up a little bit here. I'm going to combine like terms here and here. So now I have negative 9 minus 17y equals 8. I'm going to get this 9 off the left side by addition, and I'm going to add it to the right side. So I get negative 17y equals 17. And when I divide both sides by negative 17, I get y equals negative 1. So now I know what y equals. I can take that value for y, and I can substitute it back in here because I have a very easy expression for x. X equals negative 3 minus 5y. So let's go ahead and solve for x. X equals negative 3 minus 5 times negative 1, or x equals negative 3 plus 5, x equals 2. So my solution for this system of equations is 2, negative 1, which is the point at which the graphs of each line will intersect.